Welcome back, everyone, to day 3 of Charged Up Preseason Panels. We're so glad to be back, and we hope that the first 2 days have been educational experiences for all FRC teams watching. Today, we're honored to present with Reza from Team Spyder, is 1622, talking about command-based programming. So take it away, Reza.
Hello, everybody. My name is Reza Bagheri. I'm from Team Spyder 1622. Like you said, I'll be talking about command-based programming today. So just to get started, I'm going to introduce my team. So we're Team Spyder. We're based out of Poway High School, and we represent our own engineering academy. Our main program is FRC, but we use FTC as a training program where rookies come in and they learn programming and mechanical skills at FTC before they graduate onto FRC. And then they're productive members from their first season. But in reality, we do a lot more than just build robots. Our students get to be part of a real business environment, and we do a lot of mentoring, outreaches, and community service, where our students learn what it's like to volunteer in the community and help others out. So we help run programs such as the California Association for STEM Advocacy, where we advocate for increased STEM funding. It's like the California legislature. We do similar things at a national level. One of our main goals is to inspire others to get involved in STEM. And so we do that by volunteering and running events all around the world. And mentoring over 50 FIRST teams annually. We also attend over 70 outreaches, and this is kind of one of them. We're just presenting about command-based programming. So I'll keep this part short, but I'm one of Team Spyder's co-presidents. I help run our local mentoring efforts, so FDC and FL in the San Diego area mainly. But I'm also part of the programming team, so I have a lot of experience programming 3 of our robots. I helped program our Rapid React in-season robot, our Rapid React off-season robot, and the Infinite Recharge off-season, so like the 2021 robot. A lot of my command-based programming experience comes from the Rapid React in-season and off-season robots. In the off-season robot, we had a swerve drive base, a full, I think it had like around 380 degrees of total motion pretty much, and a double-sided intake. So that all that complexity kind of forced my hand to use command-based programming, which is a great thing because it's an extremely useful skill and something I would definitely recommend you guys look into. My contact information is at the bottom. It'll also be at the end of the presentation if you guys have any more questions or want any more specific help. So let's talk real quick about the conventional approach to programming. So most teams use an iterative architecture. So that means that your robot will be ticking once every 20 milliseconds, and in that tick, every subsystem gets to run its code 1 time. And so this is the time your robot that most of you probably use. You're going to have different subsystem classes, and each subsystem class has its own motors and has access to the controller, and it pretty much manages itself completely independently of everything else. So that subsystem class will figure out when you're pressing a button, and when you're pressing that button, it'll run a motor or something along those lines. Every subsystem has a single lifetime, which means on robot init, it starts up, it can do whatever it wants to start up, and it runs during periodic, and it has like some sort of shutdown procedure, which is not very common, but it can. You can do that during disabled init, but I'm not talking about that here. It's a bit of a smaller note. But yeah, it has a single lifetime, and every subsystem manages itself completely independently of everything else. So 2 of its major disadvantages are that it makes it harder to manage the robot in terms of actions. So if you're looking at your robot at a higher level in terms of like doing a complex action, such as moving the turret to some angle while preparing the hood and the flywheel to like prepare a shot, it's harder to do that with an iterative architecture because the subsystems might not be connected and all sorts of other issues we'll talk about as we progress through the presentation. And so that makes it harder to write more complex code and write, oh, I'm sorry, the lights turned on. Okay, that makes it harder to write more complex code, and that includes autos, where it's kind of essential to think of your robot in terms of actions rather than just running a motor or running something. But it also has a lot of advantages. So it's great to pick up as a rookie programmer or just as a rookie team in general. It's very simple. It's just pretty much when a button is pressed, for example, you can run a motor. You can do more complex things, and many teams do, and they did for many years, but it's still great to pick up. So it's just kind of build on the basic skills that you kind of think about. It's also very similar to how a lot of games are programmed. So if you're experienced in game development, it kind of works out. Oh, sorry. And it's also more than capable for any simple robot. So for example, we have the EveryBot on the right. So if you don't know, Team 118, the Robonauts, releases a robot every year called the EveryBot, which is a robot they do build, that costs under $1,000. And any team should be able to build it really quickly, really easily. It's meant for kind of rookie teams just trying to get into FRC so they can figure out what they can do to be like barely competitive. And so the point is that it's kind of a competitive concept that'll kind of get the job done. And so this year's EveryBot was really simple. You can see it had this kind of triangle at the top on this arm. And so this arm and triangle would go down, it would pick up a ball from the ground, and it would move up and push the ball out. So this is really simple. This can be done with 4 buttons. You have a button to move the arm up, a button to move the arm down, a button to pull the balls in, so run these rollers in, button to push them out. So that's extremely simple. So you don't really need anything complex. You don't need state management. And so you have subsystems and you bind buttons to just run a single motor in those subsystems. So that's extremely simple and it has no need for command-based programming. Another example would be if you were to look at a simple robot or like a kind of a, if you look at 1678, that's a very complex robot, but you could simplify it and think about it in terms of if it was just a fender shot. So pick up balls by running the intake, and then it would just run the indexer until balls get to the shooter and just shoot them out the top. Very simple. And if you don't have to deal with aiming, and you don't have to deal with shooting from different distances, and it's just like 2 buttons, it's really simple, and it doesn't need to deal with state management. Another major advantage of an iterative architecture is it can be switched to a command-based paradigm really easily. And so I'm not counting like actually making the commands, but just kind of getting the framework set up. And it kind of opens up options to using commands in the future. So you can do this using WPI lib system, which is really simple to add to your current code, or your own homebrew system. So for example, Team Spyder had our own system last year. And it was really, so we just built it directly on top of timed robot and it worked really well. So you can do that too if you fancy. So it's just really easy to expand and do more complex things on. Now let's talk about command-based programming. So command-based programming is a different paradigm compared to iterative programming. So the way it works is you're thinking about the robot in terms of actions. So you're going to have an action, for example, an intake action that's going to deploy your intake, run the rollers, maybe prepare the, I don't know, the indexer to pick up a new ball, whatever that may be. And so you have commands that actually do actions, and you have subsystems, and your subsystems are just wrappers. So they don't actually do anything themselves. They just prepare your motors and sensors and pneumatics to actually be used by your commands. So every subsystem will just have all the motors it needs defined, all the methods it needs defined, and commands will actually run those motors and run those methods in order to actually do things. Subsystems will also manage running commands. And so that can be done through state or through pressing a button. So the user can press a button to extend the intake, for example, and it runs the intake command, which can, like I said, maybe extend the intake, run the intake, prepare the indexer. Or it can automatically intake when it detects a ball with like a camera on the back, which some teams had, something along those lines. Or for example, a shoot command can be triggered when the shooter subsystem detects the hood is at the right position, the robot is aimed, and the flywheels are spinning at the right speed. And then when it detects everything is all ready, it just automatically shoots with no need for user input. And commands are what actually do the actions. So they have their own independent life cycles. We'll talk about that a little more later. And they claim subsystems and use those subsystems to do things. So our shoot command, for example, would take the shooter subsystem, which would have like the turret, the hood, the flywheels, and also probably the indexer subsystem. So it could actually pick up a ball and move it up from down here into the shooter. So that's pretty much how it works. And we'll talk a little more about the life cycle thing in a bit when we get to examples. So here, obviously has disadvantages. It's not all perfect. So it's a little harder for rookies to pick up. So it's a new paradigm, and it involves having a little more code than iterative, which can kind of be a plus or a minus depending on how you look at it. In some places, it actually decreases code, and we'll talk about that too. But it's overall just a little harder to pick up than iterative architecture, where a button is like directly bound to running a motor or something like that, which is really simple. And in some situations, it's actually harder to read. I would actually argue, I think this one's subjective. For me personally, it's actually a lot easier to read. But like I said, for a rookie, it might be harder. And it really depends on your level. And this is subjective. It depends on the team, the training, and what experience the programmers have. And it can also be overused and misused. Command-based programming is great, but you shouldn't use it in every situation. And if you do, it can make your code a lot more complex than it has to be, which is never a good thing. Might be cool, but just overcomplexifies your robot, makes it harder to debug, makes it hard to add new features. So here's an example of like a command. You can see this is using WPI-libs command-based model architecture. Our examples will shift between WPI-libs and Team Spyder's own command-based architecture. It's really similar. I'll explain the differences in a bit, but this is just pretty much what you would look like, what your command-based code would look like if you're using WPI-libs. You can pretty much see there's an initialize method, which is what you do when the command is called. This is kind of the start where you might be resetting the gyros in this case because we're driving. We want to reset the gyroscope for the swerve and like home or drive base or something along those lines. And then execute. This is run every tick. So every 20 milliseconds, just like in a timed robot architecture, our commands execute method is called. In this case, it's just taking the user input of the joystick and putting that into our swerve subsystem. We're telling it to drive based on the user's inputs. Now, when we determine that this command is ended, we'll talk about how we can determine that later. We're just going to stop the swerve module. What this does is just turns off the swerve module. It's just, for example, we'll show more commands later, and it'll probably make some more sense then. And is finished is where a command can determine whether or not it's finished. It's one of the ways you can finish running a command, and we'll talk, like I said, more about the different ways later on. So what are some advantages of command-based programming? So command-based programming is more like declarative programming. I wouldn't say it's declarative. By the way, if you don't know, declarative programming means you're thinking about the robot. Sorry, you're thinking about your code in terms of actions. So in terms of what you want to accomplish, what your tasks are, instead of what you're telling the computer to do. So, or the robot in this case. So you're not thinking about the robot in terms of run this motor for this many seconds. You're kind of thinking about it in terms of, drive the robot this far back. That was a really watered down example, but it's an example. It also allows you to have more reusable code. So you can use the same code in teleop, like in teleop with a button or based on the robot state, or in auto, you can just chain different commands. And in fact, this is how most autos nowadays are written from good teams. They use command-based. So they have like a command to drive, and while that's running, when they detect they're at the right position, the robot detects the state it's in and dispatches the intake command or the shoot command to actually pick up balls and shoot them. A bit of an oversimplification, but we'll talk about that more later. And it gets the point across. It also allows for better synergy between different subsystems. So let's say you have an intake, indexer, and a shooter. Your intake commands will run the intake and also kind of shuffle balls in the indexer. So you'll pick up the ball, it'll bring it into the indexer, and if it's the right color ball, it'll move it up close to the shooter, and if it's the wrong color, it can push it out, just for example. And we're also going to have the shoot command, which will fire the shooter and also take the balls from the indexer and push them into the shooter to actually fire the balls. And so the kind of like common subsystem in these two commands is the indexer subsystem. We need to have access to that subsystem. And command-based allows you to do that really easily because your shoot command and your intake command can both require using the indexer subsystem and their respective subsystems. And then they can actually use those subsystems as wrapper classes to actually do things with their robot. So kind of it allows for better synergy. If you were to do this manually, you'd kind of have to bind the same buttons. You'd have to bind actions to the same buttons in different classes, which might be a little more complicated and a little more confusing. It just kind of centralizes your code and makes it easier to debug too. As a part of that, that's kind of where the synergy comes. It makes it easier to write. It also simplifies complex actions that need to happen in order. So our example, the example code we're going to write is actually going to be kind of for an elevator. And I think we use hatches, not balls, but in this example, we're using balls. Really simply, pretty much in this game, you'd pick up balls or hatches from the ground or from the wall, and then you'd have to move them up to the right height and then push them out into these bins. There were many different heights you could push them out into. In this case, we're just using this one as an example. So you could have a command to, for example, run the intake and then drive this down at the same time. And so you could, once you detect the ball is picked up, you can immediately start moving this up to the right height while you're driving away automatically. And then you can automatically line up using your limelight. So you could run the lineup command while you're moving the elevator up. And once your all your subsystems detect they're in the right state to kind of push out the ball, you can automatically eject the ball. So it helps automate complex actions instead of having everything bound to different buttons. The operator or the driver would have to manually press the intake button, the move elevator up button, the push ball out button, all that stuff. It makes it a lot simpler and it's all automated. They could just press a button and it'll run the whole action group, all of the command group, sorry, and do everything it needs to do. So what are some situations where it might be useful? So anytime you need a life cycle for an action, we'll show an example of this on the next slide, but anytime you kind of need to be able to start a command or like start an action, do something while it's running and then end it. So if you were going to be doing this in an iterative architecture, you'd need an entire state machine, which isn't too complex to write, but it's more boilerplate code that you can't really just copy paste and you have to write every time. And then you also have to manage the states between different subsystems, and it just gets messy as you try to add complex things. If you need life cycles, it gets messy if you try to do them without command based. So an example would be homing a hood. We have code example on the next slide we'll talk about. It's also really helpful anytime you need to chain actions or run them at the same time, or kind of any combination of running commands or actions at the same time or in parallel, whatever. If you're using iterative programming, you'd need to have a state machine to manage which commands to run at which times, which works, but again, it's more complex. It's more boilerplate code. You can't just copy paste, and it just makes it a little more difficult to do overall. And again, anywhere you need to get subsystems to work in synergy, command-based programming helps out in those situations too. Let me pull this up. All right, so here's an example situation. So we're going to be talking about homing a hood in this case. So let's say you have a hood on your robot, and if you don't know what that is, pretty much if you're shooting a ball out of the top of your shooter and you want to adjust the angle the ball comes out of, you can kind of move a rack. So it's like your ball's coming out. I don't know if this camera shows, but ball will come out, and you can adjust the angle it comes out of by moving a little kind of like plate above the ball, and the ball will come out of whatever angle you define. That was not a very good explanation, but it's okay. So on the left, we have an iterative robot that's doing this action. And on the right, we have a command-based robot that's doing this action. And the question is homing the hood. So what you're going to want to do is run the hood to the 0 position to know where it starts out. So you get reliable kind of angles no matter where your hood started off at the beginning of the match. So it'll automatically home the hood to 0. It'll figure out where the 0 position is. And then from there, it can move to any position it wants relative to the accurate 0. And so the way we're going to do this is we're just going to drive the hood backwards at a low voltage until we hit a hard stop. And then we're going to detect a current spike in the motor. Once we've hit a current spike, we know that we've hit a hard stop and we can't move anymore. And we're just going to set this as the 0 position of our hood. This would be similar to having a limit switch, except you don't have a physical limit switch. You're just using current spikes to figure out when you reach your 0 position. This isn't the best way to do it, but it's a good way to do it for this example. And also the code isn't super complete. Like this isn't exactly what you would do. You'd use some more stuff to make it a lot more clean and a lot more reliable in an actual match. This will get the point across. So you can see on the left with our iterative architecture how much more code we have to write. We have to deal with this enum over here, which is the state. So when you have a state machine, you have your different states. You have to move between them. So you have to manage defining all the states. Then you have to have a place to store your state. And then here, this is the code that involves actually homing the hood and also the state machine. So you can see we're switching between states here with these if statements and changing our hood state variable, as well as actually running the motors and doing the calculations we need to do to home the hood. And so this is a lot more code than what we have on the right. On the right, we do have this entire command we have to declare. This is create. That's extremely simple to do because you can just copy paste the command. It's going to be the exact same code every single time. You just copy paste it, and then you have to write this code on the inside. This is all you really have to write. As opposed to here where you'd have to define a state machine every time and write the logic for that state machine. So it's a lot less code. And also one side note here is you also have to manage the default state. And this is where you may run into issues if you're going to have multiple subsystems using this specific part of your robot. This state is going to have to manage other subsystems, and you're going to have to figure out when this subsystem is controlled versus another subsystem. It just gets messy. You don't want to do that. And also, one thing the syntax here doesn't have, this is Team Spyder's command-based architecture. It's a little different. You can see the method names are different. The concepts are very similar. So I won't explain it too much, but pretty much you start your code here. This is what's run every 20 milliseconds, and this is what's run when the command ends. With a command-based architecture, you can claim a subsystem, and specifically with WPI libs, we have a flowchart on the next slide I'll get to. You can claim a subsystem and make sure no other subsystem can use it at the same time. This helps with synergy, because if your intake is trying to use the indexer and so is your shooter at the same time, they might be fighting for the indexer motor, and that's not going to go well, because neither subsystem is going to get what they want, and no one's going to be happy. So you can require subsystems and kind of force every other command to wait until you're done to actually use that subsystem. And we'll show that more a little later too. So how do we actually structure a command-based robot? Let's say you actually want to do this. So you have to start by creating your subsystems. So like we talked about earlier, a subsystem is just a wrapper class for your actual physical robot. And so each subsystem corresponds to a physical subsystem on your robot. Each subsystem class, sorry, corresponds to a physical subsystem. And it acts as a wrapper class. And so each subsystem will have the motors defined in it, as well as any sensors you need and anything else. And this will be in the code. We'll show you that specifically how we do that. And then you're also going to need to create commands. So each command will require a subsystem. And so what this means is this is going to be the subsystem that's actually going to be doing things with. So this is the subsystem that no other command can be accessing at the same time because they might be conflicting. Yeah, so it's going to require a subsystem. Commands will also use the subsystem wrapper class that they're requiring to actually do things. So they can either use methods or directly access the motors, for example, kind of do whatever they want to actually use the motors inside the subsystems or the pneumatics to do what they need to do. And you also need a way to register commands. And this can be done either when you press a button or based on the state of the robot or a subsystem. So you can either dispatch like the shoot command when you press a button, or you can dispatch it whenever you detect the hood's at the right position, and so is the turret, and so is the flywheel. It's really up to you, whatever you think is best. By the way, here's kind of a flowchart for requiring. You see, this is where you for dispatching a command, it talks about requiring. So this is where you dispatch the command, and then it figures out, is the command scheduled? So you can only have one of every command scheduled at a time. So your intake commands will be running your one intake. If you need to deal with multiple intakes, you're going to have to handle that within your commands, or you're going to have two commands, one for every intake. If it is, just don't dispatch the command, it's already running. If it's not running, here's where you have to check the requirements. So these are all the subsystems you have to require. If they're available, great, you can just run the commands and claim those subsystems. If they're not, you're going to have to figure out whether or not all the other commands that require that subsystem are interruptible. So what this means is you can actually define whether or not a command can be interrupted if its subsystems are required. So we'll talk about this more later when we're talking about default commands, but you actually get to specify whether or not your commands will be interrupted, or whether they're urgent and you kind of can't stop them. You got to let them finish what they're doing. If they can be interrupted, you interrupt them and you run the command that you want to run. And if they can't be, you just the command is going to run. You're going to have to run it at another time when all the requirements are available. So every subsystem will also have a periodic method. So this will also run every 20 milliseconds, but it's generally not actually used to move anything or do any actual actions. It's just used to read the robot state and figure out whether or not it should dispatch a command. So like we were talking about, the shooter subsystem can determine whether all the the hood, the flywheel, and the turret are ready to shoot. And if they are, it'll dispatch a shoot command. Or you can have it bound to a button. So when you press the button, it'll do this. Just the two ways to do it. If you're using periodic, you're probably going to be using the robot state, because there are other ways to dispatch commands just on button presses. That are simpler and require less code. So once you register a command, so you can either dispatch commands to run one time, or you can actually do a thing called setting a default command. So sometimes for example, like your server drive base, you're going to want it to have a default command that'll run whenever you're not doing something with the drive base with the command. So if you're not aiming the robot with the command, rotating the drive base, or you're not in auto, you're just going to want to run the default command that uses the joystick inputs to drive the robot. So that's going to be your default command, and it's just going to run anytime there's not another command using that subsystem. So as soon as the command is run, it's going to stop. As soon as that command is over, the default commands will run again until it's interrupted by some other command. And these are pretty much by definition interruptible, because if you ever want to use the subsystem for anything other than its default purpose, you're going to want to be able to. If you're not doing that, you're pretty much using an iterative architecture, which is okay, but it's probably not what you really want to do. So we're going to talk about an example scenario, and I guess, sorry, I was wrong in saying it was 2019. Our example scenario is going to be 2018. The example robot we're going to be looking at is 2910's robots. So they make really simple robots every year. This robot pretty much just picked up cubes. So there were yellow cubes you would pick up through this front over here. These green and red wheels would pull the cubes in. They hold the cube in there, and then this entire lift mechanism would move it up to the right height. And then the wheels would push it back out again. And then it'd repeat the cycle and pick up more cubes and cycle. So I wanted to keep it simple, but enough for command-based paradigm to be useful, so that you actually have a reason for using this paradigm, for example, in this situation. So first we have to create the subsystems. So we have two subsystems here. We have a manipulator, which is what actually pulls in the cubes, pushes them out, as well as a lift. So our manipulator, you can see we just have a motor and a sensor defined in here. These are our own wrapper classes for Neos, by the way. You don't have to worry about it. Just for simplicity, we're using these, but it's just a motor, and we can run it at whatever speed we want. So we set our motor up, and we also set up our sensor. So this sensor is just some sort of sensor to detect when we have a cube inside the robot. In practice, it would probably be a little more complex than this, but for the sake of example, it's going to work. For the sake of the example. So in this case, we're actually going to demonstrate a default command by having an instant command. So what that means is you don't actually have to create a class for every command. If it's really simple and you just need to run code every 20 milliseconds for a specific command, you can use an instant command, and it's going to do just that. So what this default command is going to do is it's just going to run the intakes of like the manipulator's wheels to pull the cubes in backwards, so it actually pulls balls in. So if you're not manually pushing a cube out, it's going to be pulling him in. So that if you have a cube in there, it's going to be pulled all the way back, and it's going to be firmly secure. And if you don't have the cube in there, it's going to pick up the cube as soon as it touches one. We also have a method to assist with our commands and make it easier for a command to be able to detect whenever we have a cube in here. It's just the method has cube, and it returns whether or not we have a cube based on the cube sensor. So the other subsystem we have is a lift. This just has a motor and a PID controller. Ignore these PID constants. They're just arbitrary. They're zeros because it doesn't matter for the example. What we're doing here is we're just going to be moving the lift motor up and down. So we're using PID. So we're going to set the tolerance. This is how we're going to figure out when we're at the right height. The tolerance is like how many encoder ticks pretty much we can be off from the target to still count as being on target pretty much, so that we don't have to be perfectly on target, and our code will still work. I actually think this is rotations of the motor, sorry, not encoder ticks, but it doesn't really matter. Pretty much just how close we have to be to the target. Then we set the idle mode. So for example, we're just going to say that the motor is strong enough to be able to hold the lift at whatever position it's at without any control loops, which in practice isn't really how it works, but we're just setting it in break mode and forgetting about it. For the sake of the example, it'll be able to hold the cube up there. It'll come back down only when you want it to. Sorry. We also have a lift height enum. And so these are the different kind of values we have to be at to be able to actually pick up a ball from the ground, which is at 0, or the scale, which is at, let's say, 100 rotations of the motor. And it's just an enum. You don't have to worry about the syntax if you don't understand it. It pretty much allows us to type ground and get the value 0, and type scale and get the value 100. So it's just a little more readable. Once we have our subsystems, we have to create the actual commands. So every command will have its own slide for this case because it's a little more code. So our first command is our lift command. This will actually lift the entire subsystem, the manipulator and the cube, up to wherever it has to be. So you can see it requires a lift subsystem. And so this is where you define that in the commands constructor, you add the subsystem as a requirement, and the kind of the robot code, the command-based architecture code from WPILib knows that, and it'll handle that kind of flowchart we were talking about earlier. And then we also just have a target height variable. This is just for the sake of you want to move your lift anywhere, so you pass in the variable of where you want to take it, and it'll save that somewhere just so we can run PID on it. Here, every tick, you're going to be calculating the PID output. So we're just doing the math to figure out what voltage we have to set the motor to, or sorry, what percent output we have to set the motor to in order to lift up to the correct height. It's just PID. We're not going to worry about that syntax. And then we set that value to the lift motor. And yeah, so that's just all we're doing in the lift commands. Just while the command is running, we're moving the lift up to the correct height. And then this is kind of important, the is finished. So this is also run every tick. And this is just how WPILib knows when your command is done executing. So it can end the commands and free the subsystem up for anyone else to use it. We're defining is finished. It's just whether or not the PID controller detects this at the set point. That set point was set here with the tolerance. So once we're within tolerance, it just returns true and we stop running the PID. You can actually see that here. Once it's finished as true, it runs the end command, the end method. And you can see here we're just stopping the motor. We're stopping the lift motor because it's in brake mode. It's going to hold its position. And until we tell until we call the lift command again, tell it to go to a different height, it's just going to hold its position. So that's our lift command. Next command we have is our eject cube command. So this command is just going to run whenever we want to push a cube out. You can see this one's much more simple. We just require a manipulator subsystem. You can see that's what this is, and that's what the add requirements is. And as soon as we start the command, we immediately start pushing the cube out by running our manipulator motor forwards. So -1 was backwards, that was for intaking. 1 is positive for forwards. And we're just pushing the cube out. And we define is finished by when we no longer have a cube. So when we start, we have a cube, so we're pushing it out until the sensor detects we no longer have one. Then we define it's over. And we're actually not going to bother ending and setting this back to -1 because that's where the default command comes in and kicks in. As soon as this command is over, that's going to kick in and it's going to set our manipulator motor to start running backwards and intaking balls again, or cubes again. So those are our two commands. Now we have to start chaining them and actually dispatching them. So this is a robot container class. This is where you actually write your code to, sometimes at least, this is where you write your code to handle actually running these commands. So you can see we have a deposit cube command here, we're calling it, and it's actually a sequential command group. So this is what I was talking about, how it makes it easy to combine different actions. So the sequential command group just runs a list of commands in order. You can use sequential command groups, parallel command groups, race command groups. They all do different things. For example, parallel will run two commands at the same time. Race will run them until the first one finishes, and that ends both of them. Also, you can do all sorts of cool stuff with these commands and these command groups. But we're just using sequential, so we'll run each command one after another. So our command group it starts with a lift command. We pass in the lift subsystem to require, and we tell it what height to go to, and this is the scale height. That's what that enum was in the first slide. Once we determine we're at the right height and this command is over, we start ejecting the cube. And once we determine the cube has been ejected, we move the lift back down to the ground. And so it's really simple. It's just these three actions. And you can probably see what I mean by saying we're thinking in terms of actions right now. We're not thinking in terms of how we're moving the motor. I'm just saying lift to the elevator, push the cube out, and then move the elevator back to the ground. And think about how easy this is for auto. Let's say you just drive back some amount, you follow this path. Once you're done following the first path, you pick up a ball, and then you shoot, then you just keep driving, then you repeat the process. Really, whatever you want. It allows you to think of in terms of actions, just like you would command another person, run, throw the ball, something like that. It allows you to think in that, in terms of those, instead of thinking about how they would actually move their hands to run, move their feet to run or move their hand to throw a ball. It pretty much simplifies it. And so this is how we define when we actually run it. We're not running this on state. We're running this when the user presses the A button. So with WPILib's command-based system, you define a button, and you have different callbacks pretty much. And so you can say when the button is pressed, you run the command. You can there's a bunch of other ones. You can say while held. So while held will run the command while the button is pressed. I think it's actually called while active continuous, something like that. There's many different things you can do to run commands based on user input. It's a lot. I'm not going to get into it right now. There's just many options. And the rest of the code is it's pretty simple. You're defining your subsystems and you're defining your joystick. And so that's pretty much all the code you would need for a really simple robot. In this case, we had Jack in the Box 2018 robot, where it would pick up a cube, move it up to the right height, and push it back out. Nothing complex, but just enough for command base to be nice. And if you, like I said, if you were to do auto, it would be just as simple to add a bunch of different actions to that. And it'd be just as simple to make a really complex auto by adding a bunch of actions one after another. Bit of an exaggeration by saying it's super simple because it's still not really easy to do an auto, but it's a lot more simple than if you were to use an iterative architecture. So that's pretty much like the gist of command-based programming. It wasn't too in-depth, but I think I got the points across to kind of explain what command-based programming is and at a really simple level how to use it. You guys can ask questions now in the chat. I'll hear them out and then we can I'll answer them. If you want to contact me through my email or Discord, whatever works better. I'll answer as fast as I can to both of those, and I can help you out with code however you want. It doesn't have to be about command-based, but I can also do command-based. So let's see what questions there are in the chat.
Okay. So I think we have our first question, which is, what is the best background color for your IDE so that you can see what you're doing at competitions?
Okay. It's really up to personal preference. I use a black color because I think that looks good, but it does not matter. It's whatever you like to do, whatever looks good for you. Yeah, just use whatever you think looks good. Let's see, are there any other questions? What is a good system for programming collaboration? So I have the stream up and now I can actually read them. So we use Git. So you can use GitLab or GitHub, anything you want really. But Git is really good because it allows you to have code open on different computers and make your changes on different computers so different programmers can do whatever they want. And then you can merge that code and combine their code and selectively choose which parts of the code you keep to actually, I don't know, have your final robot code, for example. You don't want to just still keep one person's code and throw out the other. And Git makes it really easy to merge these two code bases that are now independent and make that one final code base that any other programmer can then pull and then make changes to on top of that. And then you repeat the process. How can teams work on different subsystems better communicate? So how can teams working on different subsystems better communicate to integrate their systems together better? So command-based programming helps with that a little bit, but communication is just key. To be honest, I don't have a great answer to this one. It really depends on how big your team is. If your team is much bigger, you're going to need more complex systems. You might need like a Kanban board, a Gantt chart, a way to organize your tasks, maybe like just a whiteboard really with your different actions to list what things have to get done. And then for integration itself, this is just where you guys got to communicate and figure out, like, you have to figure out the structure. So you have to figure out what subsystems your robot has. So you might have a shooter subsystem, or you might have a hood subsystem, a turret subsystem, and a flywheel subsystem. It's really up to you. Do you want those to be separate or do you want those to be connected? And depending on your code architecture and how you guys decide to integrate the subsystems, it might be better to have them separate or might be better to have them integrated. So this really depends on your team. But you guys just have to talk about it before the season starts, how you want to organize your code so that your different subsystems will not fight each other. And like I said, command-based programming will help with that. I missed a question earlier. Are there any exclusive advantages to command-based programming instead of iterative architecture? Yeah, so it makes it easier to think about your code in terms of actions and not specific, like, small-scale tasks. So like I said in our example, we have like a command group here. So this command group is extremely helpful for not only just this simple example, but also for auto, like I was talking about. You can have a command to drive to a certain position, and then a command to pick up a ball and then shoot. And you can do all of these at the same time, or you can do them in whatever order you want. And if you need to add a new auto competition, it's no problem. You just make a new command group, and you have independently proven that every one of your commands works on its own. And because of the requirement system, your commands will not be conflicting with each other. So you can just run these commands one after another until you get your task done. It makes it relatively easy to add new autos or add new functionality that's more complex without having to deal with writing state machines every single time, and just makes it easier to write more complex code. How can teams help be more inclusive to coders? I'm not really sure what that means. Do you mean like inclusive as in like include like females and like minorities, or do you mean like how can mechanical be more inclusive to letting programming actually have control of the robot? If you can clarify in chat, I can answer that after. How much time should it take to make a full auton? It depends on your programming team's skill level. There are many tools you can use. For example, Path Planner, not Path Weaver, but Path Planner that make it a lot easier. But it really depends on your programming skill level. And also, one thing I want to emphasize: make sure your team doesn't bite off too much. I really messed that up. Make sure your team doesn't try to do something that's too hard for it. So if your team tries to do something that's way too hard, it's like realistically, they're not going to get it done, and you're just going to have nothing. Try to pick some project or some robot that's like manageable. And so you don't have to make a really complex, I don't know, 5-ball auton or like 6-ball auton that goes around the hangar. Just make a 2-ball and make it work 100% of the time, and you're great. It's better than having a 5-ball that works 10% of the time. So just do whatever you can do best, and it really depends on your team and your programming expertise to make a full auton. So once you have the framework down, making a full auton, maybe an auton could take a day. I know at our competitions, we had teams like, I think 4738 was talking about, so the Patcher bot. In 2021, they created an auto in the pits before one of their matches on request of one of their alliance partners, and their program did a great job with that and actually worked. So, I mean, if you have your framework all set up, it can take you quite literally a matter of minutes. But setting up the framework is a little more difficult. How much time would you recommend allocating to your code team before the first competition of the season? Ideally, as soon as possible. So, during the prototyping phase, they should be on it. They should be writing code for your subsystems and figuring out how every subsystem will work. And then throughout the weeks of competition season, they should be, programming and integrating all the subsystems, at least theoretically, and try to get as much time on your robot as possible when mechanical isn't working to test your integration. But you're going to want maybe like a few days at least, ideally like a week or two. Well, that's probably a little hard, but ideally a week or two, where programming has complete control over the robot, and they can test all their integrations and add any more complicated features you want to add. How do you balance time best? Let me scroll up and find the right question. Okay, how do you balance time best between auton and teleop and programming? Ideally, you have different members working on different things. So you have, some members working on teleop, some on auton. If you do command-based, the great thing is it works for both. You can write commands, and then you can use them in teleop and auton. So you can spend the entire first half of the season writing all your commands. In the second half of the season, you just put them all together in an auton, and you also bind them to buttons for teleop, something along those lines. So if you use command-based, it makes it a lot easier to handle this. Just on strictly a time basis, again, it really depends on your team and how experienced you guys are. You're probably going to want to spend a bit more time on teleop because that's most of your time, because that's most of the time of the match. But it's also great to have at least a barely functioning auto. For example, in Rapid React, you might want to be able to drive off the tarmac line to get those 5 points. So, I think it was 3 points. So that's simple. That amount of auto you probably want to do. Let's find some more questions. Are there any habits you should avoid when programming for readability or making code more efficient? So this is actually a problem I definitely had. You're going to want to make sure your code is readable, and you can do that through comments and documenting it well. You also want to make sure to try to explain your code to other people as you're writing it, so that you make sure you're not like a single point of failure on your team, and it's not like no one else knows what they're doing when it comes to the code. So it's great to have comments, make sure your code is documented well, and also make sure others know how your code works. And if someone doesn't understand your code and you're explaining it to them, they can tell you, and then you can clarify, and you can be like, okay, I have to, write better comments, document my code better. And also try not to overdo creating too many classes or writing really congested code. So if you have too many classes, the person's gonna have to jump between 20 different classes to do something really simple when they might only really bare minimum have to do one. So you're really gonna have to figure out what's the right balance. So yeah, make sure you don't overdo anything. So don't have too many classes. Make sure you have more than enough comments. Don't make all of your code comments, but comment as much as you can to make it helpful. And just make it really simple to read. Making code more efficient, honestly, I don't think that's too much of a big deal in FRC programming. You pretty much want to try to make sure you're not doing too many you're not doing any like recursive functions that call themselves too many times, or you're not calling too many for loops within other for loops. That's kind of basic stuff. And in reality, it's probably not going to hurt you too much because um, it's all right if your code loop overruns a little bit, and if it does, like you're going to be fine. So really, that shouldn't be your first priority. As your programming team gets more experience, you guys are going to pick up these skills naturally over time as to how to make your code more efficient, and you're just going to have to apply them to your code and your code base. I can't really explain them to you right now because it really depends on how your code base works. Let's see other questions. Make sure to use loads of guard clauses. Yeah, please don't do that one. Okay. Let's see. Okay. Reza, how do I code faster? I'm running out of money for Red Bull. I don't think you should listen to that Chief Delphi thread. I don't think that's the play. Although I like how the chat has just evolved into the people from the San Diego FRC Discord. Does anyone have any more questions here? How to make code efficient? Yeah, I guess that works. Also, I'm gonna have to agree with Ben here. I think green narwhals are a bit better than blue narwhals. That's kind of a big deal. Uh, and yeah, I think. Does anyone else have any more questions here? Should I code in LabVIEW or Python? Vika, I think you code in Java. I think you should stick to that, and it'll be fine. Yeah, I don't see any more questions for now. I'll be here for a bit more if you guys want to ask questions, but I also have my contact here, so if you want to reach out to me here. Thank you guys for coming. Okay, no, Mika. Thank you guys for coming today. I think Alex might do an outro over here or something along those lines.
Absolutely.
Whatever really works for me.
Yeah, Reza, thank you so much for your amazing presentation. We got lots of questions, so obviously this is a very popular topic. I think you helped out a lot of people, especially with our team watching today as well. I think a lot of FRC teams kind of don't value or have this like understated appreciation for coding, and obviously it's what makes the robot run, right? So thank you so much for your presentation. Thank you to Team 1622, Team Spyder for supporting us within this week of Charged Up Preseason Panels. Just a great presentation. Thank you so much. And we do not have another panel for today, so this is the last one of the day. Thank you for all that asked questions, and we will come back tomorrow with 2 more panels for you guys at 5 p.m. again. So again, thank you so much, and we hope to see you guys tomorrow.